Now we're going to talk about the two forms of the inductor equation and get familiar with these things. I'm going to do some examples to show you how the inductor equations work. So we know that the inductor equation is the voltage across an inductor is a factor called L, the inductance, times di dt. So the voltage is proportional to the slope or the rate of change of current. Let me do a quick review of the two letters that are used as variables for inductors. When we have a resistor, we call it a R, and it's in units of ohms, and that's named after Ohm himself. And when we have a capacitor, the units are C for capacitance and F for farad. That's named after Michael Faraday. And for the inductor, we have two other letters we use, L and H. And L is the name of the component, and that's named after Lenz, Heinrich Lenz, and he did some research in induction. And the unit is named after Henry. And so that's the corresponding R, C, and L are the names of the components, and ohms, farads, and henries are the units. Okay, let's get back to our inductor. There's another form of the inductor equation where we write it in terms of just I in terms of V. And to get to that point, we need to get rid of this derivative here. So what I'm going to do is take the integral of both sides of this equation. So we take the integral of V with respect to time, and that equals L times, take the integral of di dt with respect to time. And these two terms go away, and we have the integral of di. The antiderivative of di is what function has a derivative of di, and that would be just I. So let me flip this all around here now. I'm going to write I on the left side equals 1 over L times the integral of V dt. Now we always put limits on this integral, so the limits in this case are time goes from minus infinity till some time now. And this tells us that the current through an inductor depends on the voltage across that inductor for the entire life, all the way back to time equals minus infinity. And that's not so convenient. We don't want to track the inductor's voltage back that far in time. So what we'll do instead is we'll say, let's say at t equals 0, that we know the current, that we know some I of 0. And then we can change the limits on our integral here to be 0 on the bottom. 1 over L, integral from time is 0 until now, time t, big T, of V of t times dt. In order to account for everything that's happened before time equals 0, we'll just say what was the current at time equals 0. So that's I of 0. And I'll do one more little change. I want this variable up here to be small t, and that means I have to replace this t inside here with some other symbol as a dummy variable. And so now I'm going to get I of t, little t, 1 over L, integral from 0 to little t of v d, let's just call it tau, plus I of 0. So this is the integral form. There's the integral form of the inductor equation, and here is the derivative form. And we'll use both these. What I'm going to do now is we're going to do an exercise where we use this one down here. So in our circuit, we have a voltage source with a time pattern voltage in it. And we have a current going through this thing, and we want to find out what's this current. So we're connected to an inductor. It's a 10 millihenry inductor, and the voltage waveform is it starts at 0. At time equals 0, the voltage goes up to 2 volts. Then after 2 milliseconds, it goes to minus 2 volts. After 2 more milliseconds, it goes to plus 2 volts, and on and on. So we know V of t, and what we're going to figure out is what's I through in the inductor. And to do that, we're going to use our inductor equation here, the integral form of the inductor equation. So I actually need some room on the screen here, so let me take a second and clean out some stuff. Okay, we're ready to go. So let's look at what's going on here before time equals 0. So in the before state, we're going to make an assumption. We're going to assume that I is 0 a long time ago. And if we look at our chart here, it says that V is 0 as well. And if I take this fact and I look at this equation right here, if V is 0, L is some positive number. So we can say that, so then we know that di dt equals 0. So this circuit is pretty much doing nothing before this waveform starts working. Over here, I'm going to make a little time chart of what we discover. That's time, and this will be current here. So before time is 0, we can say that the current is 0. Now we've plotted in part of our curve. Okay, now something happens. Now the voltage goes up to 2 volts, and we're going to use this equation, the integral form of the inductor equation, to figure out what happens to I of t now that voltage has changed. So we can say that I equals 1 over L times the integral from 0 times 0 is our starting point here, to t, sometime t, of V of t. Now V in this little region of time here is 2 volts, plus 2 times d tau plus I0. And we decided I0 was the current that it started at right there. I0 is 0. Let's keep working on this. We can say that I equals 1 over 10 millihenries times the 2 comes out of the integral. And now it's the integral from 0 to t of d tau. The 0 goes away. That equals 2 over 10 millihenries times what? What's this integral evaluate to? It evaluates to t. Integral of d tau between 0 and t is t minus 0, or just plain t. So looking at this, I see that I equals a constant times t, and that's the equation of a line. That's the equation of a line if I plot it on t and I. So 2 over 10 millihenries is the slope, and to plot that line, what I need is 2 points on the line. I know one of the points already. I know one of the points is going to be right there at 0, 0. What is the current at the end of this pulse here? So at 2 milliseconds, let's figure out what the current is. And that equals, at 2 milliseconds, it's 2 times 2 milliseconds divided by 10 millihenries. The millis cancel themselves out, and I get 4 over 10, or 0.4, what? Amperes. So at 2 milliseconds, the value of the current is 0.4 amperes, and I can draw a straight line between there. So now we have the value of the current during this first excursion, this first part of the voltage waveform. Now we're going to switch again. Now we have a new I0. Let's go to a new point here. Let's go to a new point at, now we have I0 equals 0.4, and we have V equals what? Now it goes to minus 2 volts. Minus 2 volts. So let's use our inductor equation one more time with these initial conditions. That tells us I equals 1 over L integral from, what's the new point? 2 milliseconds to t. And V of t after 2 milliseconds is minus 2 volts, minus 2, d tau, plus, now we have a starting current. Our starting current was 0.4 amps, 0.4 amps. And let's continue on here. Let's, maybe you can squeeze it in here. I equals 1 over 10 millihenries times minus 2 times the integral from 2 milliseconds to t of d tau plus 0.4 I equals minus 2 over 10 millis times, what is this? It's t minus 2 milliseconds plus 0.4. And again, we have the equation of a line. This is the equation of a line. There's a constant times t. There's and followed by a constant. And this is basically a sloping line. It has a negative slope, and the slope is negative 2 over 10 millis, which is just the opposite of what we had over here. We had 2 over 10 millihenries. So it's the same looking kind of line. So let me mark out here. Here's 4 milliseconds. And it's going to be a line that looks like this. So the current's going to ramp up. It's going to turn around and ramp straight back down because the slope up and the time up is the same as the slope down and the time down, just with a negative slope. So there's an example of the inductor equation in action.